So good morning all. In this next probably 1.5 hours, I'll take you through some of the fundamentals that are required from the linear algebra perspective for machine learning. And in that, what we're going to do is we're going to focus more on what are called as subspaces associated with the matrix. Say A M cross N. And let us assume that the matrix is going to be a real matrix. So before we even get into subspaces, I just want to get you the idea of what are called as vector spaces, and then we look at subspaces of a vector space. So the first thing that we even look at before getting into this matrices and all, we look at what are called as vector spaces. So we look at vector spaces. So the first place, what is a vector space? So the question is what? So now what we do is, first of all, we consider this, let's say I have a real line. Now what I do is, from this real line, a real line, as far as this vector space is concerned, it goes by another name, which is very fundamental mathematical structure to a vector space, which we call it as the field. So what I do is, I create, let's forget about this field business and all, we straight away jump into this vector spaces. So what we look at is, we're going to basically construct a mathematical structure. Construct a mathematical structure how do we construct the structure? What are all this? So from the set of real numbers. You could also have complex field and all those things, but we will restrict ourselves to real field from the set of real numbers. So how do we construct this? What are the properties that the structure should have? So how do we construct this? So first thing what we do is, step one, make, let's say, n of R. So what do we mean by saying n copies of R? Say, for example, if n is equal to 2, then we say that we're going to look at what is called as R2. This is basically the Cartesian product of R with R itself. This is Cartesian product. Okay. So now what we do is, we're going to make n copies of R, which means now what I'm going to get what is known as R to the n. This is basically Cartesian product of n such R field. So n such real field, you make copies of them. And now what we do is, second, each element in Rn we define as, say, x is an element in Rn implies we're going to have x1, x2, xn. That means I'm going to have n real numbers arranged as components of arranged as above. So xi is called the ith component of x. And we say that x is a vector in Rn. That means it basically contains n components. Now, so first what we did, how do we construct this? The question was what are vector spaces? We said that, look, there is going to be a set of real numbers, and from that set of real numbers, we are going to construct a mathematical structure. The next question was, how do we construct that structure? We said that, okay, you create n copies of the real numbers itself, make n copies, and now what you do is, from each of those n copies, you take one real number, and then put it in this form, then you say that, look, I have an n component vector. Now the question is, after this, what are the properties that, so now what I do is, before going to what are the properties, now what I'm going to do is, I'm going to look at a collection of such n vectors, n component vectors. So collection of such n component vectors. Now, what do we mean by this? I'm going to make a set V which contains x of the form. Okay, we'll put x is equal to x1, x2, etc., xn, and every xi is an element of R. Okay, for I is equal to 1, 2. So I'm going to make a collection. I'm going to make a basket. I'm going to make a box of this n component vectors. Now, what are the properties that this collection should have? The collection should have the following properties. So the first property is this collection V must be such that A, we take two elements from if x and y belong to V, that means that is x is an n component vector, x1, etc., xn, and y is an n component vector, y1, etc., yn, then x plus y will be equal to x1, etc., xn plus y1, etc., yn. This is equal to component-wise addition we do. We say that x1 plus y1, x2 plus y2, etc., xn plus yn. X plus y is equal to this is also an element. This is x plus y. This is also an element of V. For example, let's consider this. For example, if V is the set of all two component vectors, now what do we mean by two component vectors? That means V is basically equal to R2. So I'm going to have any vector here is going to be denoted as x1, x2. So what this says, I'm going to take a vector x which is of the form x1, x2. I'm going to take another vector y which is of the form y1, y2. Now I add these two fellows, x plus y. This is equal to x1 plus y1, x2 plus y2. x1 plus y1 is a real number, so I'll put it as x3. x2 plus y2 is another real number, so I'll x4. Okay. Now, this fellow also has the same structure as what we have for x and y, and therefore, this fellow also is an element of 2. Is this okay? That means what we are trying to say is, we want to say that this set V closed under vector addition. It's closed under vector addition. So the first property that for this set V of vectors, or the collection V of vectors, is that if you take two elements from V and add set V, so that's what we call as closure addition. The second thing that we are going to look at is, suppose if X is an element of V and is any scalar, any real scalar, then Kx is equal to K into x1, x2 must be equal to Kx1, kx2. Now, this element should also be an element of V. That means this implies that it is closed under. I mean, it could be for any n. So I'll just put it as xn, kxn. So this is closed under scalar multiplication. Okay. So if it is, so the second property that we ask for is the set V must be closed under scalar multiplication. And the third property that we ask for is V must contain the zero vector. What I mean by zero vector? This simply means that this is the n component 0, 0, 0, etc. 0 n component vector. If these three hold, then we call the set. We say that the set V is a vector space. Vector space for real field. Oh, important. If we do not specify what, then it is a problem. So we need to say it is be vector space over R. Is that okay? Now let us consider quickly. We'll take one or two examples and then see what happens. I'm going to look at one example now. Let's look at this. Consider the set of points. Let us say S is equal to the set of points where the vector is going to be of this form 0. X is a okay, x1, 0, x1 is a real number. Now I want to check whether did I mention this? K is real scalar. Okay, fine. So I want to check whether this is a vector space. Now what will I do? The first thing is I'll take two such vectors. Let x1 and 1, 0 be elements of S. They are naturally elements of S because they are x2 x1 plus 0, which is the same structure as an element of S. Therefore, x3 is S, which means S closed vector addition. Is it okay? No. S is closed under vector addition. Now, I want to look at scalar multiplication. Let me see what scalar multiplication actually means. So let us take for some scalar k, any scalar. Just a minute. So for k, any scalar, now I'm going to look at what is kx. K is x is nothing but x1, which is also an element. Yes, that simply means this set X is closed down. Scalar. Third thing, if x1 is equal, then 0, 0 is an element of S, or let's say over. This is okay. Any questions that we have till now? Yeah. If there are any questions, you could probably interrupt me and then ask.
So we shall take the questions at the end. Participants can put the questions in the chat box.
That's what you're following? Okay, fine. No problem. Yeah. Okay.
Sir, I think the audio is slightly low, sir.
Is it
If
okay now?
possible, yeah. Okay.
Is it fine now? Hello?
Yes, sir. Yes,
Yeah.
sir. It's audible.
Okay, fine. Yeah. So this is closure. This is an example of a vector space. You have, again, you have, it's not just over R. I mean, you could even have vector spaces of matrices. For example, let's consider this example of all real symmetric matrices. Real symmetric matrices of dimension 2. I'm going to look at all 2 cross 2 matrices, set of all real symmetric matrices of dimension 2, they form a vector space. Now, this is the question. Now, when I define S to be the set of points x is equal to x1 comma 0, geometrically, if I see, this is going to be a point, this is going to be the set of all points passing through the origin, and this is basically by x-axis. X-axis. Therefore, what is it that we are seeing x1 axis itself by itself is a vector space. This general comment. In R2, the following are vector spaces. The following are vector spaces. What are they? Entire R2 is this zero vector. This is a vector space. These two are called as trivial vector space. These are called as trivial vector spaces. And C, any line passing through the origin. Any line, suppose if we take R3, if we understand R2 and R3, I think I'm getting. Can you please mute? In R3, entire R is a vector space. We already knew R2 is a vector space here. Therefore, any plane yeah, is this fine now? Hello? Is the audio okay? Is the audio okay?
Yes, sir.
Yeah, I think I'm getting a lot of background noise, madam.
Yes, sir. The background sound.
Yeah, I don't know. Can you please ask the participants to mute themselves? Or you can mute all the participants. Yeah? Okay, we'll go ahead. Hello? Hello? I think I'm still getting a lot of disturbance. Hello?
Audible, sir.
Yeah, okay, fine. In through the origin space. Now, said, yeah? said that in R2, any line passing through the origin, therefore in R also the same holds. Any line passing through the origin, passing through the origin, vector space. These are the properties of your spaces that you have. Okay, is that vector space? So you have lines passing through the origin. There are infinitely many lines passing through the origin, which means you have infinitely many vector spaces in R2. You have infinitely many vector spaces in R3 because you have lines passing through the origin as well as planes passing through the origin. Therefore, you have lots of vector spaces as far as R2 and R3 is concerned. But the problem with this R2, R3, all those things is that, see, there are infinitely many vectors. See, if we take as such R2, there are infinitely many vectors, and it is difficult to handle this infinity. Whenever you have very large number, it is very difficult to handle. So what do we do? What do we do? We basically look at uh, trying to break that set. See, for example, I have set of positive integers. Set of positive integers is infinity, so I cannot handle that. So what do? I basically say that, okay, I can classify or I can categorize the set of integers to two sets, basically one that is divisible by 2 and one that is not divisible by 2. So the ones which are divisible by 2, I call them as even integers, and the ones that are not divisible by 2, I call them as odd. This, therefore, I basically say that, look, the set of integers has now been partitioned into two. And I know the characteristics of these two sets. Of course, these two themselves have infinitely many numbers, many integers, which I'm not really worried about. But then I have categorized these two sets into, okay, one which is divisible by 2 and the other one which is not divisible by 2. The same way, now what I want to do is, in this case of vector spaces also, I want to look at subset of vector spaces. So I want to look at subsets of vector spaces. Okay. Now, what should the subset of this vector spaces be? It's not just, it should just be some collection, but the subset of vector spaces should be, I'm looking for all those subsets which can be vector spaces themselves. Also, what I'm going to look at subspaces of vector spaces which are vector spaces by themselves. That means I'm going to look at a subset of points in a vector space, and those subset of points, or that subset of points should basically be closed under vector addition, closed under scalar multiplication, and must contain the zero vector. So now I'm going to do this subsets of vector spaces which are by themselves vector spaces are called, I have a name for this, so I'm going to call these as subspaces. Professor Ashok will be talking about in the afternoon session. So we are going to we are going to look at in close view about these subspaces. Now, for example, in this case, if you take the first example that we took, this set of points, x1 comma 0, let's look at this, example 1. So example 1. So let's look at example 1. What was example 1? We said S is the set of points x, which are x1 number. Yeah, this is the set of points that we looked at. Now, this x1 comma 0 is not just the set of points. It does not cover all the points in R2, right? It only covers all those points which are on the x-axis. Therefore, S is basically a subset of R2. A subset of R. What we are going to do? We have already proved that S is S. Example 1. Therefore, we want to say this. We say that S is a R2. this clear? So basically, we must understand one thing. If you take a vector space, take a P, and you take any subspace S, subspace and its complement will help you partition V. Is there clear? Subspace S of V and its set. After all, if it is a set, I can look at complement of the set. So complement of S. Of these two give you the vector space. Now the question is, can the complement of the can a complement of a subspace be a subspace? So question: can subspace be a space? Any answer? Anybody wish to answer this question? Someone answer this question. Is the complement of a subspace itself? No, it is not a subspace. Let's say S contains. Let's assume that S contains. I mean, S contains a zero vector, right? So S contains zero vector. What about S complement? Complement is the set which contains all elements which are not in S. Therefore, S complement does not contain zero. Contain zero vector. The moment it has to be a vector space. So therefore, okay, complement is not a vector space. Now, how is this related to a matrix, or what is it that we're going to look at from the matrix perspective? Before even looking at that, first of all, let us look at one more topic in this, and then we'll look at the what do you call the matrix perspective of all this, the subspaces associated with matrix and stuff. Now, I have a question. Are there exist, let us say, in any subspace or a vector space So what we do is we just forget that the origin being that vector space. This is the small thing that you can get. Forget about this. That just contains that element. Whereas if you look at any other vector space, I'm going to have infinitely many elements. Okay. Now, suppose if I want to transform this entire set of vectors, if I want to transform the entire set of vectors, or if I want to apply kind of transformation on the entire set of vectors in a vector space, now I have to apply it on each and every fellow. I don't really know what will happen to each and every fellow because every fellow is going to behave in a funny way. So how do I get to know what is the general behavior of the entire set of vectors? I need to get that. In that case, I not really play around with all the infinitely many vectors. Instead, what I do is, instead of playing with infinitely many vectors, what I do is I choose that is exactly like what we have. See, assume that we have some 130 crores population or something. Now people say that, look, you have 30 crores population. All 130 crore of us are capable of becoming prime minister and chief minister and MLA and MP of this country. But then not all of us go. So what do? We basically send one representative from among us, right? So we choose a representative. Now, how do we choose this representative? How do we choose this representative? We choose this representative in such a way that another example. See, all of us would be working in, let us say, our, let's say, in a college or university or somewhere. Now, we're working in some college or university or somewhere. Now, the problem is all the students in your college can become student representative or student council chairman. But what do? We choose one fellow from each and every department, and then from that set of fellows, you choose one more fellow and say that, look, you are the head for all the entire student council. The same way, I need to choose representatives. So how do I choose it? I have to choose based on different behaviors, right? Say if I want to look at an exit poll, I want to make prediction based on exit poll. I cannot go and tell that, look, I have chosen only the set of people who are academicians. I have taken their opinion and then I'm going to extrapolate their opinion to everybody else in the country. No, that's not going to happen. So what I should do, I should be taking one person representative from each and every field, and then I should take representatives from each and every field, and then I must extrapolate it. That's the best way of doing. The same way, here I choose this representative vectors in the following. What do? I choose one vector in each direction. I'll tell you what it is. One vector in each direction. This means if we take R2, there are fundamentally two directions. There are fundamentally, let's say, two, what do you call? Two values correspond, two coordinates basically. Two coordinates in sense I have x coordinate and y coordinate. So let's say two coordinates. Say x1 and x2. So now what I do, corresponding to the x1, I will choose one and I'll choose another one. So x2. So what I do is, these representative vectors are chosen. However, those representatives, I choose those representatives what are called linearly independent. What do we mean by linearly independent vectors? Geometrically, all this means is I must find 2 points on two different. Find vectors in different directions. Points on for example, R2, 0 and 1. Vectors. Now, any vector x or y is x. Any vector xy can be expressed as a linear combination of these two. Linear combination means alpha into a vector plus beta into another vector, where alpha and beta are scalars. Now, 1, 0 is along the x-axis, 0 is along the y-axis. These two are linearly independent vectors. So, what we're going to do is, we're going to make this definition. Any set of k linearly independent vectors span. That means their linear combination of these k linear independent vectors will give will span. Say this will span k. You can say vector space or a subspace or whatever, k dimension space. And these are what are called as base of space for k dimension. Now, what is interesting is if you have k linearly independent vectors, it will span a k dimensional subspace. Therefore, these two count. The number of vectors inside a basis, the basis set, is the same as the dimension of the vector space that it will span. Is this okay? Any questions still here? Linear independence. Okay, fine. I'll just do that. I'll just do that linear independence. Okay. So what we mean by linear independence? Of course, I have the two vectors. Consider u is equal. Now, what is linearly independent? For example, I will give values 1, 2, and v is equal to 3, 4. Now, I mean, afternoon session, we'll show all the visualizations for this. Sahil and I will sit together and then we'll show all the visualizations for this. But then we'll try to understand now what it means. Now, what does this mean? If we take this 1, 2 is a point here, 1, 2. 3, 4 is basically, this is 1, this is 3. Let's say 1, 2, 3, 4. 3, 4 basically a point. No, it's a point here. Now you see that line L1 and this line is L2. These two are on two different lines. Is this clear? The vector, this is 1, 2, and this vector is 3, 4. These two basically they operate in two different lines passing through the origin. Is this okay? Yeah. So mathematically, how does this look like? Mathematically, it simply means this. What does this mean? It says alpha into 1, 2 into 3. To get a zero vector out of this. In the only way to get zero vector is by making alpha is equal to 0, beta is equal to 0. Okay. This is. So how do we define? We said 1, u2, etc. uk are k linearly independent vectors. The only way to a zero vector is a combination alpha 1 2 k equal alpha. Now I'll bring the matrix perspective of this. So what does it mean? Let's consider this example A. Alpha into 1, 2, B. Two linear equations. What are the equations I'm going to have? 2. I'm going to have this alpha 3 beta equal to 0. 2 alpha plus 4 beta is equal to 0. Okay. Now, if I try to solve a system of equations, what does this? I'm going to get 1, 2, alpha, beta. This is 0, 0. Now you see what is it that I'll get? This will only this determine this matrix is A, and this is equivalent to X, and this is equal to B. Is a determinant of A is not 0. invertible implies please 0. We say here alpha is equal to 0 and beta is equal to 0. That's the only solution to homogeneous system of equations. Is this okay? With this, any questions still here? Any questions? Okay, so let's go ahead. I hope. Now you see we have clearly come to coupling both the matrices and the vector space stuff. How is the coupling basically done? You see, if I take any system of equation Ax equal to B, this is the system of equations that I have Ax equal to 0 in this case. Let us put some other B. So let me take x plus 3x2 is equal to B1 and 2x1 plus 4x2 is equal to B2. Now, this example should have made something clear. What is that clear it's making? The first column always gets multiplied with the x1 component, and the second column always gets multiplied with the second component x2. The same way, I'm going to put it here. Say that x1 into 1, 2 plus x2 into 3, 4 gives me b1, b2. Now, what does this mean? This is equal to, again, I'll put it the equivalent matrix form is 1, 3, 2, 4, x1, x2. This is equal to b1, b2. Is this okay? Is this fine? Here, you see the determinant of A is not 0. Therefore, the matrix is invertible. Therefore, what does it say? For every B2, you can find scalars. This is called combination of the vector, linear combination of 1, 2 and 3, 4. Is this okay? So what does it say? If I have an invertible matrix, for every B1, B2, B vector that I give on the right hand side, I can find scalars x1 and x2. Now, this definition of your linearly independence also tells us something. What does it tell me? It says a linearly independent set, therefore, cannot have the zero vector at all. Is that clear? That will write us about linearly independent set. Number one, cannot have the zero vector. Then, vector, say for example, I want the zero vector on the other side. So I want to 1, 0, 0. I can tell, I'll put alpha as a fantastic. But I can also I can have 0, I can have alpha equal to 0 and beta is equal to 6.023 into 10 power minus 23 or 10 power 23, whatever that number that is. Give me the zero vector, which means this set, therefore, the 2 and the 0 linearly independent. Is this clear? Any question? I will come to this. Orthogonal matrix, I'll come. Don't worry. All your questions are answered. Okay. Now you see, suppose I take a 2 cross 2 matrix. Suppose we have A2. Yep. And I want to look at the system of equation. Let us consider this A matrix to be 2, 4. And I want to look at what is 0. Basically the homogeneous equation. So I want to look at 1, 2, 4, 1, x2. Now can you tell me the solution for this? Solution to A equal to 0. Can someone give? See, it would be nice if you can put the answer here, because only on interaction I will be able to give my best to get you the, I mean, to tell you the concepts. If I don't get the answer, because already you're all muted, I don't want it to look like a monologue where I come deliver some lecture and then go off. A into x1 plus 1 into x2. What is A? I want a number. I want the values for x1 and x2. Can someone give me the values for x1 and x2? If you solve the system of equations, can I get the system? Plus 2 x will give me x equal to 0. Is that right? This will give me the answers. x1 equal to x2 equal to minus 1. That will also. X. That means, you see, too many things are happening here. But can you tell me what is happening here? There are definitely to this equal to 0. The solution. The solution, if I try to plot the solution, it's going to be like this. What is the solution? X equal to 0, 0 is a solution. X1 is equal to minus 2, x2 is equal to plus 1. Say minus 1, minus 2, minus 3. Let's take 1, 2, 3, plus 1, plus 3, 1, minus 2, minus 3. So what is this? X1 is equal to minus 2, x2 equal to minus 1. So this fellow is here. This fellow is here, 2 comma minus 1. Then what is it? X1 is give me. Okay, x1 is equal to, let's take 3, and y should be equal to, I mean, x2 should be equal to minus 1. So 3 comma minus 1.5, which is somewhere here. You see, the solution for this system of equation falls on this line. Is that right? So the system of equations, yeah, both are linearly dependent. Of course, they are. Very good answer. Now, question is, set of solutions fall on this line. But what is the nature of this line? This is a line passing through the origin. What did we claim about a subspace in R2? Any line passing through an origin, passing through the origin is a subspace of R2. Therefore, we say that set equal to 0 is, and that subspace goes by a name, null space. It also goes by a name called kernel. Is this okay? Is this okay? Are you guys getting this? Is everybody getting this idea of null space? See, I still have some more ground to cover. I'll try to do it, but please let me know if you've been able to, if you've understood what I'm saying. See, the set of solutions. See, I want to look at the solution equal to 0. Ax equal to 0 has infinitely many solutions. Any solution of the form -2, 1 and a multiple of that will be an answer to Ax equal to 0. Is that right? And the moment I say there are multiples of this together, the set of points will be one line passing through origin at -2, 1. Therefore, all points of this line will be, this will be equal to that given Ax equal to, what is that? 2, 2. X1, X2 equal to 0, 0. Is this okay? Now is it clear? Yeah, Mahesh, is that clear to you? So this is called the null space. Now, what does this null space do? Null space says, look, you take any point on this, the point is line. If you apply the transformation A to this, you take A. Put this, all the points on this line to this dabba. This dabba is say, look, I will get you back to this particular. I will transform everything to 0 vector. Is this clear? You do whatever you want. This is like the most, what do you call, anything that you do that goes to 0. Is that clear? If you put very, what do you call, an unsatisfied professor, any good student goes to him, he will still say, oh, so what? You are a bad guy. Put here. It will be put onto the 0 vector. Is this clear? So, null space is nothing but, let's write that now. Null space of A, nothing but set of solutions to Ax equal to 0. Now, R2 incidentally does not just have only the points on this line. It also has points outside this line. Here, here, here. It also has points here. It also has points which are very close. Here, this and all. Where do these points go? They go get transformed to something else. Is that clear? So now what I'm going to do is I'm going to make a small definition out of this. I'm going to say for various values one of x1 x2 b this could be extended to any n component vector. I'm just taking 2 components because it's easy for us to understand and visualize. So I'm going to write this as x1 into the first column of A plus x2 into the second column of A. Is this clear? So I am going to call this set of vectors. So I'm going to call set of B1, B2, which can be expressed as linear combination of columns of A. I'm going to call this set as a column space. It is also called as ray of A. Is that clear? Let's take a simple example from functions perspective and then come to this example. Suppose I give you f of x is equal to x squared, and x is a set of natural numbers. Right? What and what is the domain of it? Is basically a set of natural numbers. So what is the range of f of x? Range of f of x is basically a subset of this n. Numbers are basically 1, 4, 9, 16, 25, 36, 49, etc. That means only these numbers can be expressed as x squared. Is that clear? Only those x squared. 3, the number 3, no, I cannot find an integer whose square is 3. The number 2, I can find an integer whose square is 2. 5, I cannot find an integer whose square root 5. So these numbers don't come into the range. So what we say, the range of f of x is basically a subset of this set of integers which have the form x squared. The same way, I'm going to define a range of a basically set of x can be expressed as linear combination of columns of it. Let's go back to the same example. We had example 2, 1, 2, 2, 4. Now the question is, what is the column space of A for this? So let us see what this is. So the first column is 1, 2. The second column A2 is 2, 4, which is basically 2 times 1, 2, which means A2 is also essentially A1 itself. Is this clear? Therefore, B, which is of the form B1, B2, I want to look at what are all the B's which can be written as. But this alpha times A1, alpha times A1 is alpha plus B times A2, beta is nothing but 2, 4. But 2, 4 is equal to 2 times 1, 2. So I'll take it as alpha times 1, 2 plus 2 beta times 1, 2, which is nothing but alpha plus 2 beta times 1, 2, which is nothing but say some gamma. So any vector which is multiple of 1, 2 can only be represented as B1, B2. Suppose I take gamma is equal to 1. Let us again look at where is this 1, 2, and 2, 4 geometrically. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2 is basically this point. 2, 4 is basically this point. So let us look at this. 1, 2 is, where is 2, 4? 2, 4. 2, 4 is also along the same direction. This is the vector 2, 4. This is 1. This. But where is 1, 3? 1, brilliant. 1, 3 is somewhere here. This is 1, 3. Let us see where is that 1, 3 direction. 1, 3 direction is this. You're getting it? 1, 3 cannot be expressed as, because 1, 3 is in a different direction as 1, 2, and 2, 4. 1, 3 cannot be expressed as a linear combination of 1, 2. Therefore, what we say, 1, 3 is not in. Is everybody clear with this? Any questions? Yeah, let's go ahead. Two subspaces for a matrix, fundamental subspaces. One is called the null space of a matrix, and other one is called the column space of a matrix. Similarly, with A, if I do two subspaces, I can also do two with A transpose. Therefore, with any matrix A m cross n, just a minute, excuse me. With any A m cross n, we can identify four fundamental subspaces. So, what are the four fundamental subspaces? Let's first of all look at only square matrices right now, but I'm just moving on to a higher dimensional rectangular matrix. Where we say that m is not equal to n. Okay. In this case, I want to look at A m cross n, x n cross 1, gives me 0 n cross 1. This is what I wanted to look at, the null space of A, right? So in this case, null will be the set of such that Ax is equal to 0 m component vector. That means null space A is a subspace of Rn. Similarly, I want to look at the column space of A. What is column space of A? This is nothing but set of B vectors, B in Rn, A m cross n into x n cross 1. That means a set of all those x vectors which get transformed to this B vector. Therefore, column space of A is a subspace of R. Is this clear? So, if I have to write it properly, I will visualize it. Again, we'll always look for visualization and try to understand from there. So, what we see is Rn, I have Rm. So, the matrix A, see it is like this. I have this matrix A, and then I have this matrix. So this is basically null space of A. This is null space of A transpose. This is range of A. This is range of A transpose. Is this clear? So all my X vectors live here in Rn. All my B vectors live here in Rn. Is this clear? Is this fine? Is this fine with everyone? Yeah. We go ahead. Any questions? Okay. So, what is this matrix basically doing? If you want to go from R to Rm, I use A. If I want to come, I use this vehicle. If I want to come from Rm plus Rm to Rn, I use this vehicle, A transpose. Okay. Now, what is this matrix A doing? A matrix is very intelligent. It is like a knife. You take this knife and you cut. It does two things. It cuts Rn into two parts, wherein one is a subspace and the other is not. And it cuts Rm into two parts, where one is a subspace and the other is not. What does this mean? Whenever you take this A knife and then you cut, it is like a cake having multiple layers. Okay, let's assume that you have multiple layered cake, or it's like you can even take this. You take a scissors. See, whenever you want to cut an envelope and there is another envelope inside that. So what you do? You use the same scissors and then you cut the outer envelope as well as the inner envelope. It's exactly what is happening. So it will cut Rn into this is a subspace and Rm into this is a subspace and something else which is not a subspace, because we said a subspace and I mean, if you have a subspace, its complement cannot be a subspace. So Rn basically is cut into a subspace and something which is not a subspace. Rm is basically cut into a subspace. So these two are as a result of the matrix. Then what we have, I want to do something similar to this way. So what I do this. I take the help of A transpose. I cut the matrix, I cut the Rm into two parts. One is a subspace and one is not a subspace. And this are by virtue of A transpose. Similarly, I will use A transpose as a knife to cut Rn into two parts. One is a subspace and the other one is not. Is that clear? So basically we have four. Is this clear? Any questions still here? Any questions? No. Okay. So let's go ahead further. I mean, we asked the R is the only subspace associated matrix. Only spaces of matrix. There are linear cases that can associate with the matrix A. Look at one specific case of A where I'm going to look at A n cross n. See, I'm just trying to go back and forth between m cross n and m cross n and m cross n, square and rectangular matrix, because there are certain good things that happen with square matrices which don't happen with rectangular matrices. So I want to look at this. So now what I do is I look at this matrix, 2, 1, 1, 2, and I look at this vector 1, 0. What happens to this? This fellow says, look, I'm going to give you 2, 1. I want to look at this matrix 2, 1, 1, 2 and ask you this question. What happens to this? This fellow will say, look, I'm going to be this. You tell this fellow 2, 1, 2. Oh, fine. I will give the same number 2, 1. So what is this? I'm going to get 5, 4. Then I'll say 2, 1, 1, 2 and then multiply it 1, 2. So it says, no, look, I will give you 4, 5 now. I'm going to give you one more matrix, 2, 1, 1, 2, the same 2, 1, 1, 2, acting on 1, 1. This is giving me 3, 3. I'm going to give this one more, 2, 1, 1, 2, into 1 minus 1. This gives me 1 minus 1. This is quite interesting. See, input I gave this. This is like Virendra Sehwag playing this cricket. You bowl any ball, he flick it around through the entire ground. That's what I don't even know. 1, 0 was along the x-axis, 2 is somewhere there in R2. 0, 1 was along y-axis, 1, 2 is somewhere in R2. But you see, these two vectors alone, they behave very well. If I give 1, 1, the output vector is basically in the same direction, but it is stretched by a factor of 3. This vector is stretched by a factor of 1. All right? Is this clear? Now let us apply this 2, 1, 1, 2 again on the 3, 3 and see if E undergoes any change again. 2, 1, 1, 2, 3, 3. This fellow says, look, 9, 9. Oh, this is brilliant. This is 3 times 3, 3. This is nothing but I have applied 3 times 1, 1. Is that right? Which is basically, and what is this? This is 2, 1, 1, 2 applied on 2, 1, 1, 2 applied on 1, 1. This is a squared is equal to 3 squared into 1, 1. See, I'm quite sure most of you during your with your parents. So what does your kid do? As soon as he or she sees a nice doll there in the shop, the kid will start asking you, Mom, can you please get me this? Our first reaction to anything that the kid asks is no. Why will you want to go and give a doll which the kid, I mean, when typically what we feel is like we should not give them immediately when they ask, because they'll not know the value of the doll. So first of all, what does the kid ask? The kid is very dumb to ask the mother, because father at least will get. Mother is always that strict person, he will not get. So the kid asks the mother, Mom, can you get me this doll? Mom says, no, I won't get you this doll. Then what does that kid do? It won't leave. It will start pulling the mom's dress, saying, Mom, please get me this doll. Mom will grow a bit angry, saying, look, no, I won't get you this doll. Third time, the kid will start crying. Again, the mom will not get the doll. Fourth time, the kid will start crying even more. Everybody around will start looking at you. What he will do? One slap on the kid and then saying, shut up and come. Now the kid will shout even more. You will see all the neighboring aunties and all coming and giving you a suggestion that, why do you want to make this kid cry? You get him the doll, all those things they'll say. The same thing is what is happening here. Suppose if you assume this 2, 1, 1 mother and 1, 1 to be the kid. So the first time when the kid asks you for a doll, if you get it, it's fine. If you don't get it, it is already a naughty, violent kid. It has now increased its, what has it done? 2, 1, 1, 2. It has basically gone from 1, 1 to it has already become violent. It is 3 into 1, 1. Right? Second time, on that violent kid, now the mom is again playing around. Look, I'm not going to get you. This is becoming 3 square. On that more violent kid, the mom is again saying, oh, that is becoming 3 cube, and so on. So for this transformation called mother, this vector 1, 1 is what we call as eigenvector. Is that clear? The magnitude by which the kid increases crying, or the intensity with which the kid cries, that we call as eigenvalue. Is this clear? It is the same mother who is trying to transform that kid again and again. But the kid says, no, I will never transform. I'll grow more violent. He gets beaten. And the first thing is like he cries because he doesn't get the doll. And second thing, the mother also hits him. And the kid starts crying more because it is the pain of not getting the doll and pain of getting beaten. And in front of everybody, everything adds to it, and then it cries more. That is exactly what your eigenvector does. On the other hand, there is one more fellow who has seen this kid getting beaten. He'll ask you, Mom, can you get me this doll? Mom says no. Okay, fine, I won't cry. Again, he'll ask, Mom, can you please get me this? The fellow says no. If you don't get third time also, I'll try it. I will do all like what Gandhiji did. I will do non-violence, no shouting, nothing. I'll keep asking you. If you don't get it to me, fine, I will still remain the same. Finally, you will get fed up. See, 10 times the kid has asked me, I have not got the doll, but let me get it, because he's not even crying. He's such a goody kid, so we'll get it for him. So what we are looking for is, if in case of a n cross n, we are looking for that vector xn cross 1, which is basically lambda times xn cross 1. Whatever input that you put it to this dabba called A, the output is a scaled version of it. So this version is what the scale is, what we call as the eigenvalue. This x vector, which is here and here, this is what we call as eigenvector associated with the matrix. Now, what is interesting is, if I look at the direction in which this goes, all the values, a squared is along the direction 1, 1, a cube is along the direction 1, 1, ax is also along the direction 1, 1, nothing changes, right? Nothing changes, which means these eigenvectors invariant, they don't direction change. So whenever you have a matrix A, n cross n, diagonalize matrix A, diagonalize A as P, D, P inverse, where P is the eigenvector matrix, which contains all its columns to be the eigenvectors. D is a diagonal matrix whose diagonal elements are all eigenvalues corresponding to these eigenvectors. P inverse is basically the inverse of that matrix. And what is interesting is, matrix, if you take a real symmetric matrix, A, what does this mean? So what does this mean? A transpose equal to A implies it's a real symmetric matrix with distinct eigenvalues. It is very interesting. Distinct eigenvalues with distinct eigenvalues corresponding to distinct eigenvalues. Let's put this has eigenvector this orthogonality, very, very important. What is the property of orthogonal matrix? Somebody had asked. Orthogonal matrix basically has this property. What is the property? Column orthogonal to each other. Each column or has unit length. What do we mean by unit length? The column vector has unit length. Now, in such cases, if you have an orthogonal matrix, is interesting is the inverse of A is the transpose. This is the most important stuff. Inverse of A is its transpose. And if A is an orthogonal, I want to look at AX. Look at AX. A orthogonal. The B that you get, AX equal to B, this B you get, it has the same length as A. Same length as A. Same area as same length as X. Same shape as X means what? Suppose matrix to which I put a square as the input, which means I give 4 coordinates of the square. The resultant B that I will get will also be a square. For any other matrix, if I take 2, 1, 1, 2, and let me put the square 0, 0, 0, 1, 1, 0, 1, 1, I'm going to get numbers which are 0, 0, 1, 2, 2, 1, 3, 3. So now if we try to plot this, what will happen? 1, 0, 0, 1 is basically this. This is the that I have. It's not a square. Rectangle. Let's redraw that. So what we have is 1, 0, 0, 1. So this is the unit square whose coordinates are here 0, 0, 0, 1. I mean 1, 0, 1, 1, and 0, 1. This, what does it get changed to with the 2, 1, 1, 2 matrix? That's more important. 2, 1, 1, 2 matrix, this is 0, 0. 2, 1 is here. 1, 2 is, let's say, here. And 3, 3 is here. You see, the shape that we get is completely oblique. The shape. Okay, so your orthogonal matrices are important because they preserve the profile. They preserve whatever information that you have in X, it will preserve in the resulting vector also. Is this clear? Now the question is, whenever I have a square matrix with n eigenvectors, I can PDP inverse. But I don't have this luxury of square matrix all time. So I only look at A m cross n. In that case, what do I do? I cannot diagonalize no eigenvalues and eigenvectors. They're not even defined. No eigen, nothing is defined. So what do? I look for what is called as singular case. I write this V sigma U transpose, where V is M cross N matrix. Sigma is M cross N diagonal matrix. That is an abuse of terminology because diagonal matrix should contain equal number of columns and rows, but I'm writing it as M cross N diagonal matrix. Then U transpose is basically N cross N matrix. So why do I call this as diagonal matrix? I'm going to have a part of this, which will be a part of this. A submatrix is going to be diagonal. Of the fellows are all going to be 0. So this is going to be M cross N matrix. So I'm going to have M. How many non-diagonal elements I'm going non-diagonal elements have? Let's say R. So where R is rank of the matrix. Is this clear? And what is interesting is SVD exists for all matrices. It is irrespective of the shape of the matrix. It could be a fat matrix, it could be a thin matrix, it could be a tall matrix, it could be a matrix, it could be any damn thing. SVD exists, whereas decomposition exists only for square matrices. And even the number of eigenvectors is equal to the number of columns. Otherwise, it does not exist. So a more generic way of understanding a matrix or what a matrix does is through SVD. So find the SVD. There are computationally efficient algorithms available for SVD. In the afternoon, we'll also see the application of SVD in image reconstruction and stuff. We will also look at more visualizations as these linearly independent thing is concerned, then what is happening to this oblique stuff. All those things we will see in the afternoon. Orthogonal matrices, everything. Is that okay? Any questions? I can take up questions now. Any questions? What are the applications of SVD? That's a very good question. See, I mean, as Gilbert Strang says, your linear algebra actually begins with SVD. Okay, your linear algebra basically begins with SVD. SVD has wide range of applications. The first application, most simplest thing that we would probably look for is, let's say I want to solve a system of equations. See, it is like we say, no, you go to Kamadhenu or and then you ask for something very trivial, what do you call, blessings from this Kamadhenu. So it's like the first thing that we want is like I want to solve AX equal to B. A is an M cross N matrix, B is an N cross N matrix. Now what do I do? A now, many a times, this B may not be in the column space of A. I don't even know what will happen. If it is not in the column space of A, typically we say that the solution does not exist. But if a solution does not exist, then you cannot simply say, look, I won't work this problem out, right? It is like saying, look, I want to come to Mangalore University and conduct this. Right now, the situation does not prevail where I can come to Mangalore University and conduct this workshop. So what do I do? And even on a normal day, I would always say, look, there is no one particular conveyance which is going to pick me up from my drawing room in my house and then put in the classroom of Mangalore University where this workshop is happening. Right? So I can say no solution exists, therefore I cannot come. But what do? It's okay. I will walk certain distance from my place to the nearest railway station or whatever. I'll take a train and then come to Mangalore City Railway Station. And from Mangalore City Railway Station, I'll pick another conveyance. I'll come to the entrance of the guest house or probably the classroom. I cannot make the train come to come and drop me there in the, classroom where this is happening. So I have to minimize the distance that I walk, right? So we have, if you want to find the least square solution, you want to find out, solution to a system of equation, all you do SVD. With SVD, we get what is called pseudo inverse, A pseudo inverse, which is given by V. Okay. Now, what is this V sigma inverse U transpose do? If I want X equal to B, I don't want to do this AX equal to B because it is M cross N. The inverse for this M cross N is not defined. Therefore, what I do, I use this. I get X is equal to A pseudo inverse B. Is this clear? So what A pseudo inverse B does is very interesting. The sigma inverse, you don't worry about places it has zeros. Wherever you have the non-diagonal elements, non-zero diagonal elements, there alone you put it as 1 by sigma 1, 1 by sigma 2. You put all that. These diagonal elements that you have, sigma V transpose, this diagonal elements, these are called as singular values. Oh, that is singular value. X is equal to A pseudo inverse B. A pseudo inverse, you get it through SVD, and it will help you get what is called as, if you have least square, get you the least square solution. If you have a unique solution, it will actually get you that unique solution. So it is one way used for solving system of equation, number one. Number two, you will actually see when we do this PCA and all in the afternoon, when we do SVD based reconstruction, image reconstruction, PCA based reconstruction, we need only fewer dimension, when it's like saying I do a data compression and then I try to reconstruct using a compressed image. So you can do that. Third thing, most important thing of SVD is that when you look at random variables, when you look at Gaussian distributed, jointly Gaussian distributed random variables, SVD, if you apply it on that covariance matrix of your Gaussian random variable, see, only in case of Gaussian random variable, we know that uncorrelated Gaussian implies independent. In all other random variables, independence will imply uncorrelated, whereas in case of Gaussian alone, uncorrelated will become independent. So what we do, I want to make two Gaussian random variables to be independent. That independence I can get by doing a simple rotation. So here again, you are going to do your SVD business. Is that okay? So SVD has a lot of potential applications. Orthonormal basis function.
So there is one more
That is
question.
good. What do we mean by orthonormal basis? Yeah. I'm just checking that. What is orthonormal basis function? That's what I'm asking. How do we define basis in terms of functions? Right? And how do we define orthogonality in case of functions? See, orthogonality in terms of vector spaces is vectors in terms of vectors is very easy. You take the dot product of these two. Therefore, what you'll get, if you take the dot product of these two, the dot product should result in 0. For example, you take this vector 1, 1 and take the vector 1 minus 1. 1 into 1 plus 1 into minus 1 will give 1 minus 1, which is 0. But in terms of functions, what should I do? I take two functions and then do an integral dt or whatever the period or whatever the interval limit minus infinity to infinity or that period. Just check. That should give me 0. If that is 0, then the two functions are orthogonal to each other. Suppose, then what do you mean by orthonormal in that case? That's a good question. What do we mean by orthonormal in that case? What do we mean by orthonormal functions? Suppose I take this. T and cos t. Right? Are these orthogonal functions in the first place? Of course, over a period, if you integrate, it will become cos 2 sin 2t, and then you integrate sin 2t over a period, the resultant is 0. So this will be orthogonal functions. Orthonormality is what? What is orthonormality? Then we'll go to this basis function. Do we define orthonormality? Can someone answer? That's a very interesting question. Vectors are normalized. Functions, how do you normalize? Functions, how do you normalize? Vectors, that's exactly why I keep asking this question. If it is vectors, it is all easy. The vector should be unit length. It's a unit vector basically. Functions, what do we do then? Any answer? Okay, I'll do one thing. You guys think over it. Anyway, I'm going to meet you at 3:30 along with Sahil. We will discuss what an orthonormal function at that time is. Just try to figure out what it is. If you're not able to get it, I'll give you the answer at 3 o'clock or 3:30, whenever that is. Okay?
Okay, sir.
Yeah.
Participant, if the